Okay, thank you very much. I'll spend the next 25 minutes giving you a glimpse um, of materials modeling and have used machine learning in materials modeling the past 10 years, and then again try and conclude with some open problems, what we're thinking about now. So let me start off where Giuseppe Carleo ended yesterday, which is he introduced the Schrödinger equation. Let me see if this pointer works better. Yeah. So you can all see it. So h psi equals e psi is how the world works. We know h. It's actually very simple. The problem is that this wave function is a very high dimensional object. And so exactly solving this equation for anything but the small systems is very, very difficult. It is, however, variational for the lowest eigenvalue, E0, and that's partly how people actually do try to solve it. But what this equation represents and its solution is the behavior of the electrons, the electronic structure when you have some given molecule with its atoms in a fixed position, or you have a crystal with its atoms in a fixed position. But actually, that's just part of the problem. So when we want to understand how materials work, atoms move around. We are not at zero temperature, fortunately. And what you discover is that the nuclei are very heavy, so about 2,000 times heavier than electrons. So they move very, very slowly. So it's actually a very, very good approximation to think of nuclear positions and then the electrons go into the ground state, which is a hard problem. And then you want to move the nuclei by some small time step, perhaps. And then you have to solve the electronic problem again. Here's a little movie of a piece of water. And what you see is the electronic density. This is an isosurface of the electron density, which basically follows around how the molecules move. So the molecules are moving. They're not rigid. They vibrate. But the electrons essentially follow the nuclei. But when we solve this in practice, we have to resolve the electronic problem every single time when we change the nuclear positions. But in fact, so that's a huge waste. And what we should really be doing is considering this equation as a parametric equation for the electronic problem, where the Hamiltonian depends on where the nuclei are, right? The nuclei just provide the electrons with a Coulomb potential. And so if you had a black box that gave you the solution of this Schrödinger equation for each positions R, then that would lead to a function, the energy of those atomic positions. And that's what's called an interatomic potential. And that's actually all we need to understand how almost all material processes work, how finite temperature materials behave. So the quantum problem is in there, hidden in the value of this function, E0, as a function of R. But we're not actually, almost all the time, we're not actually interested in what the electrons do. We're interested in the whole material and how the atoms explore this potential energy landscape. And if you had that potential energy landscape, you can solve for the nuclear motion, either using Newton's law, that's commonly called molecular dynamics, or in fact, you can solve Schrödinger equation on the nuclei, and some people do that when they need to, right? So then they solve the nuclear Schrödinger equation, where this E0R is simply the potential in that Hamiltonian. But you need this function in any case. So let me just show you again a little glimpse of how expensive it is to get this E0 of R for a given set of nuclear positions. So I'm showing you the cost of a single evaluation for a bunch of different systems. So if you take a methane dimer, which will be later one of my examples, and you do something called density functional theory, which is one flavor of one approximation to the Schrödinger equation, it will take you 1 minute on all these numbers are for single core, single CPU. And that it scales as n cubed. So if you take 30 methanes in a box, it will take you 100 hours. And different atoms have different numbers of electrons. Actually, it scales with the number of electrons. So if you take 50 iron atoms, it's again about 100 hours for a single evaluation of that potential energy function. DFT is not good enough necessarily, and certainly for methane it isn't. So you can go beyond DFT, get a better approximation of the Schrödinger equation, something called couple cluster theory from quantum chemistry, and it will take you 1 hour to get the energy, potential energy of 2 methanes. And that scales as order n to the 7. So you're not going to do, well, you might do 3 methanes, but you're not going to do 4 methanes very often. There are also other methods that go beyond DFT. There's quantum Monte Carlo. It scales as order n cubed, but it has an enormous prefactor. So if you want to want to get the potential energy for 30 methanes, it will take you many, many years of CPU, single CPU time. And people do that once or twice for benchmarking. So here's the sort of simulations that we would like to do. Here's just from my own very recent work, 7,000 iron atoms as iron is being corroded by atomic hydrogen. So this was not done with quantum mechanics because it has 7,000 atoms and we needed to evolve the atomic positions for many, many thousands of time steps. So we're not sure whether what you see is actually really right. Here's another example. This is 50,000 iron atoms. And this, what you're seeing is a screw dislocation. I've removed most of the atoms from the pictures because it's a big block of solid. But what you're seeing is a line defect, a topological defect in the crystal. And it just sort of hopped over. Let me see if I can write it again so you see it. It sort of hops over by one atomic layer. And that's a process we would like to simulate quantum mechanically, which we can't because it has 50,000 atoms. And then one of the largest simulations that has been done fairly recently here in the US on the Blue Waters machine is the molecular dynamics of a viral capsid. So that was 64 million atoms simulated for 1 billion time steps. Okay, so clearly you're not going to do it quantum mechanically, but these researchers wanted to do it atomistically with that level of detail because they say that if you mutate one amino acid in that protein, it will actually change how that capsid behaves. And in order to see that, you need the atomic detail. So it's clear that what we need is analytical models. So quantum mechanical modeling, explicit quantum mechanical modeling is very useful for understanding the very fundamental nature of pieces of matter that are homogeneous and small or very small molecules, but we're not going to make big progress if we insist on simulating the electrons. So empirical force fields and interatomic potentials are approximations of this E0R. And for the past 50 years, people have been writing down various analytical approximations of that, essentially just mostly by intuition. Let's see how accurate these need to be. So a typical enthalpy of formation is about 1 to 10 electron volts. That's how much energy you get when you put atoms together. If you want to think about a reaction, something breaking, a bond breaking, that involves around 10 or 20 atoms in the vicinity of the bond breaking. And kT at room temperature, that's the typical energy you have available that controls whether you're going to make that jump or not, is 0.025 eV. So if you multiply and divide those numbers in the right way, so about 100 EVs divided by 0.025, you get about 1 part in 10,000 as the minimum required accuracy. So we're going to need to fit this E0 of R, which we can calculate for selected examples at some cost, minutes or hours. We need to fit it with 99.99% accuracy to actually get the right physics. So typical parametric modeling, which is what people have been doing for 50 years, doesn't reach that. So here's a molecule, and you take something like a bond length and a bond angle, and you write down some analytic form for the contribution of those, how the potential energy should change as a function of that, and maybe it's a quadratic, because why not? That's Taylor expansion. And then someone tells you that actually there's Coulomb interactions. Okay, I know the form of that. It's Qi Qj over Rij. If I knew what the Qi's are, I don't, but Why not? And that's how people have been building models. And this only works for a fixed topology, right? So if I know where the bonds are. And just to, again, a little bit, the last context slide is that all of this activity takes up significant HPC time in the world. So this is what I found is the last year's report on 2 years ago on the Blue Waters machine as application workload. And the red bars here are all interatomic potential simulations of mostly biology. And this is a log scale, right? So this is 100 million CPU hours for the highest one. So about a third of the time is taken up by interatomic potentials. The green is explicit electronic structure. So it comes much lower because it's so expensive, but also partly because it doesn't scale to many CPUs. And so Blue Waters is actually not people don't use it for electronic structure that much. But here's on the lower one is a more representative of your average HPC machine. This was the UK national machine so about 6 years ago. And about a third of it is electronic structure. And that's typical for the similar US machines as well. So if we could make electronic structure faster or interatomic potentials more accurate, we would be impacting the science that people do in supercomputing. So this is the end of the introduction. I'm now going to give you a few slides on how we've been thinking about this problem. There's a small community that has grown up over the past 10 years in trying to do this. In this very short talk, I don't have time to give the right credits to my friends and competitors. So here's how we think about it. There's a representation problem. So the potential energy of atoms is a function with a variable number of arguments, because if I take more atoms, I have more coordinates. There are 3n atomic coordinates that I need to describe. And this potential energy function has invariances. It has symmetries. And symmetries have, earlier in this workshop, have come out as a very strong constraint that one can put in from physics, and we're going to do that as well. So it's the potential energy is invariant to rotations and permutations of like atoms. It also has very strong regularity. And the regularity properties and how we put them in, I think, is critical to success. So we start by doing a range separation. So if we had to consider all the atoms all the time, then I don't think we would really make any progress. So we take long-range interactions are actually the Coulomb interaction, for real, even in the quantum Hamiltonian, and so we can use the analytic form for that. And then for the short-range interaction, we can use kernel and neural network regression to regress the remaining terms, the short-range terms, to calculated reference data. So again, this was emphasized by Carleo in the first talk, yesterday in his talk, that this is not experimental data. We're fitting to reference data, and in some sense, from a broader experimental perspective, this is zero information from nature. We're really creating models with which we then simulate. And we have E0 and the gradient of E0 available. The energy must be extensive. So if I double the system, let's say in periodic boundary conditions, then the energy must double exactly. If that doesn't happen, then all sorts of problems happen in the simulation. And so this has been done for decades by essentially doing what convolution over atoms. So we write the total energy as a sum over atoms of some local energy function centered around the atom of interest plus long-range Coulomb. And this local atomic energy think of it as hidden variables, hidden parameters, right? That's a function I want to infer, but I don't have observations of it. I have observations of the total energy. And with a bit of playing around, you realize that the dimensionality of this local energy function is about 100 dimensional. That means you have about 30 neighbors which significantly influence the energy. So we're going to use kernel regression. And here's the kernel that we've built up over the last few years that has served us very well. So we're going to represent the neighborhood of an atom. Here's an atom. Here's the cutoff. And within it, there are some atoms. And we're going to represent it as a density. And it's a Gaussian modified density with a finite cutoff. And then the kernel between two different environments, that's what we need to do kernel regression, is going to be the overlap between these two densities. And that solves permutation invariance. But we also want to solve rotational invariance. And we're going to do that by integrating this overlap, the square of this overlap, over all possible rotations. So this dr hat is integral over one of the environments over all possible rotations as we multiply and integrate. And that six-dimensional integral would be quite nasty to evaluate if we had to evaluate it explicitly, but fortunately we don't, because a piece of harmonic analysis and work of Rishi Kondor shows us that if we expand this density in spherical harmonics, then what we realize is that a square of those spherical harmonics, C dagger C, is called a power spectrum, P, and this K turns out to be just P dot P. So this K that we defined as a rotational integral of the square overlap of densities is actually exactly equal to P dot P, where P is C squared. So that's a very nice piece, very nice result from harmonic analysis, but it turns out to be an amazingly good kernel. And it has really very few free parameters. So it has this sigma, the modification, how wide our atoms are, and we know that the potential energy surface doesn't change very rapidly as we move atoms around. We have a cutoff, and that's again a user input, how far we want to treat the interactions, and a linear fit in K isn't quite good enough, so we use a quadratic, a little quadratic kernel. So these can be generalized. I won't spend much time on that. Multiple atom types, even multi-scale by changing the cutoff and the modification, and that's been spurred by discussion with Stefan. So let me show you examples. I want to show you two little stories. The one and one of them, the first one is it's very recent, the equation state of fluid methane, and it's sort of very educational because it shows us why we want to get the right answer for the right reason. Why do we want to go beyond empirical modeling? So methane as a fluid at low temperatures and high pressures is dominated by weak dispersion interactions between the methane molecules. And we don't know what level of quantum mechanics is actually required to describe that. And we don't know if considering pairs of methanes is enough. That's what people have been doing for the last 30 years. So here's a pair of methanes. Here are the two methanes, and on the horizontal axis you see the difference between the distance between them. And on the vertical axis, the black curves show you the grand truth. So that's for different curves correspond to different orientations of the methanes. And right, so it's different, and and it matters. If I orient the methane differently, the separation curve is different. And this red curve is the simplest potential that people have been using to describe. It's some sort of crude average, rotational average. But of course, one can make that more accurate. So still an empirical model, this red one, and what I'm showing here is the error. So note here the scale is, goes up to say 0.1, and here the errors go from sort of 10 to the minus 5, and these errors on the red model are significantly better and are significantly smaller, and we can make the blue model, which is what we made, the errors are down to 10 to the minus 3. So we can make these black curves, fit these black curves very, very accurately. But what happens when we actually take this model and simulate the density of methane? A big box of methanes, so every pair of methanes interacts like this. So, so here's a bunch of different empirical models that people have made. And what I'm showing you here is the averaged error over these curves. And you can see that different models take this error from 30 down to 10, or even down to 3. And if you look at now what happens in the density, so this is a box of methanes, on the horizontal axis, I actually show you this error on the dimer, and the vertical axis is the error in the density, where 0 is the experimental density. And what you see is that all of these empirical models actually get the density pretty much right, irrespective of what their error is, and actually describing the interaction of pairs of methanes. Why is that? That's because these models were fitted to reproduce the density. What happens if we say, actually, let's get the right answer for the right reason? If I fit the pair of methane energies really, really accurately, I should be getting the density really, really accurately. But that doesn't happen. So this model, the one that's best on the dimer, actually is pretty poor. And we can make an even better model. So this is the zoomed in scale, and this is half a milli-eV, so 10 to the minus 4 on this scale, invisible on this scale, and it's terrible. it makes it 50% error, 20% error on the density. So that tells us that these models, these empirical models, get the right answer for the wrong reason, and if you try and fix them, the answers become worse. And that's because it's only considering 2 methanes. And everyone thought that that's enough. But actually, when we consider the neighborhood of a methane with all the other ones there, with the kernel method that I showed you before, we get a different picture. So here's a series of models, and now their accuracy on the dimer goes down, and the corresponding accuracy on the density gets close, it goes down as well, goes up and gets closer and closer to the real density. And the difference between these models is now not the regression, but the level of quantum mechanics that we use. So the way we did this is we separated the total energy into a one-body energy, a short-range energy, and the dispersion energy. Each of those got fitted using kernel ridge regression, using the kernel that I introduced, and we're getting accuracies of 0.1 millieV, so 100 micro EVs accuracy, really very exquisite accuracy on the interaction of these particles. And the red curve, this red set of symbols is the best model that we could come up with, and still there was a 5% discrepancy, and that's when, instead of tearing our hair out, we started simulating the nuclear Schrödinger equation instead of Newton's law. And that, quite unexpectedly for this system, turned out to be the missing last 5%. So if we really go all out, do the best quantum chemistry we can, regress it with this good kernel and kernel ridge regression, and then it's fast enough to solve the nuclear Schrödinger equation on top, we actually get the equation of state of methane. So these yellow points are right on top of experiment, and for the right reason, because we are actually getting the potential energy surface right. And then we can then take this model and look at other things, which that's sort of in progress, viscosity and other properties. So the other example that I would like to show you is a materials example, and we call it the silicon challenge. In the materials world, it's the material that everybody starts to simulate because we know very much about it, what are the different forms of silicon and what the defects are and what the surfaces should look like. And here's just a picture of all the different crystal polymorphs that people over the years have come up with. And there's a huge diversity. All of these are pure silicon. Let me draw your attention to these 2 different groups. These are liquid snapshots, and these are amorphous snapshots. Amorphous silicon is a technological material for sensors. And in fact, the way I made this map, this is a multidimensional scaling map using the SOAP kernel that I introduced. And what that tells you is that this is a very good sign. It actually separates liquid structures from amorphous structures structurally without any dynamics. And that's, in fact, that's new physics already, because people, as we heard yesterday, don't know how to think of an amorphous and a liquid structure independently. So the problem is that this took us 10 years, and this is a monster database. Of course, I'm not expecting you to read the numbers, just be horrified by how many different hand-picked categories of configurations we needed to do. The numbers are all different because these were all data was gathered by hand. So little simulations were done. When the queue time ended, then we just used whatever we had and so on. So it's very, very ad hoc. We end up with about 500,000 pieces of data, gradients and energies, and we picked 9,000 basis functions. So we have a rectangular kernel ridge regression. That's the same as a sparse GP, so 9,000 sparse points in our Gaussian process. And we end up doing really quite well. So the red model is us, and this is fractional error with respect to our ground truth, so quantum mechanics, and the other bars are the state of the art in empirical modeling. But it's not all rosy. There are configurations here which have up to 10% error, and that's because we stopped building our database. We didn't really design the database for them, and we can try and use the variance of the GPs. So that's the predicted error, to see if the model knows where it's going wrong. And that's sort of true. So here is a vacancy, here's a missing atom, and what I'm coloring the atoms by is the predicted error, the variance of the GP. And what you see is that it's all blue, it's all very good, and indeed the error is very small. And then we go to these configurations, and these are the structures where you have these planar defects in the crystal, and the database, fitting database, knows nothing about structures like this. And indeed, we see that the variance of the GP jumps by a factor of 5 or more. So these were the two examples. We have started making successful applications. So we're no longer researching machine learning only. We're actually going out to the material scientists and saying, you can simulate growth of amorphous carbon, which is, again, a technological coding with our models, and get the right answer and infer why that happens. We can simulate amorphous silicon, find new structures of boron, phosphorus, iron, titanium, phase change materials that is in your Blu-ray discs, germanium, antimony telluride. So all of these, just in 2018, have been applications of materials modeling enabled solely because we have fast and accurate machine learning models. I'm out of time now, so I will not discuss the protein ligand binding effect, but just one sentence that this applies to molecules as well. And we have successful applications for molecular modeling. I want to finish with some thoughts on the current challenges. So there are scientific challenges and there are engineering challenges. I think the thing that really vexes me in terms of the science is better control of the fitting error. So if you asked me what should be the right measure of error in, say, fitting silicon or any other material, I really can't give you a mathematically precise answer. I would start by citing applications, and different applications need accuracy in different parts of configuration space. And that's a real problem because we don't really have a good way of translating that into an error measure. Extrapolation away from the training set is problematic. Silicon is sort of the best case we have, and even there are problematic problems. There are problematic issues. And this sort of brings us to this dichotomy of, are we doing approximation theory? Should we be talking to people who have theorems about polynomial fitting and other linear basis fitting? Or should we talk to the statistical inference people? We have noise in our, very small amounts of noise in our data, and we've actually used, most of our heuristics are taken from the statistical learning literature, not from approximation theory. And I'm sort of really caught between those two words. We are simulating with the ML model. So this was again mentioned by Carleo yesterday, that this can lead to exponential error amplification. We're not applying the model to a given distribution. Nature is throwing configurations at us. We are simulating with the model, and if there are errors in that model, those can grow exponentially. We really want to learn parameters of the Coulomb interaction. That's sort of the next technological step. In terms of engineering, what I'd like to have, and these are what I think of as the 5-10-year challenges, is that given a material composition, I'd like to have a protocol that tells me how to generate a database, how to train, and how to validate it, so that the model can be used by scientists without them having to be experts in all of this. And then a more restricted but wider impact challenge, I think, is to really go after the organic force fields, replace the current organic force fields with something that's reactive, can break the bonds, and is accurate, and so it can be used for biochemistry and catalysis. I think that would make probably the biggest impact in atomistic simulation. Thanks very much for the attention, and happy to answer questions.
Kernel ridge regression, like random forest?
So I haven't. There are other, this is a community, and again, in this sort of short overview, I didn't introduce all my friends and competitors. Other people have tried, mostly neural networks, shallow neural networks, like 2-layer neural networks. Random forests, we haven't tried, and are you thinking about using it to decide which variables to use? So it's a
interactions. We add stability to random forest.
Is that also, I mean, these are continuous problems. Is that?
You can also do classification. Yeah, continuous should work too.
Okay, I'd be interested.
I'm not sure I understood how you proceed, because when you deal with a new system, you first have to generate a database to train, and so you first need a model to generate this database.
That's quantum mechanics, Schrödinger equation.
But if you have a very complex system, you cannot really.
Well,
you're back to the question you.
No, so what happens is that this is where the locality comes in, right? So what we need is this database. Okay, let me illustrate that on the silicon. This is a database, and look at the number of atoms in each of the calculations. They are about order 100. So these are small unit cells that represent the local environments that we might encounter in a big simulation. And then we take that database, we regress it, and then we do a million atom simulation where all the local environments are hopefully represented, and we do this atomic convolution. So we apply the function we learned in the local environments to every atom in the big system.
Okay, thank you.
And that can be done. Even for a thing like a protein, locally, the atom doesn't know that it's in a protein at that instant, right? All it sees are the neighboring couple of covalent bonds.
Okay, thank you.
Yeah, so not for the examples that I presented here, but of course, electronic structure modeling does use those where and when required. So when for modeling systems where it's known that those effects play a role, one can do that. So if you want to take for example, if you're interested in the electronic structure of a semiconductor and you put in a dopant atom, actually you need, and that electron from the dopant is going to fill some band, and that band does depend on spin-orbit coupling. And so you need a version of the Schrödinger equation which takes account of spin-orbit coupling. So all of those things are, for me, are kind of mature tools that come with guidance on which to use when. The fact that for methane, I can't use density function theory, but I need coupled cluster theory, you need to have done a PhD in chemistry to really understand that or know that. But it's in the books. So there is a whole hierarchy of electronic structure, all the way from very crude, essentially a Huckel model, right? Just electrons as little as points hopping between sites, all the way up to full configuration interaction, actually solving the real many-body Schrödinger equation in all its glory. In these examples, machine learning is useful for us when we have 1,000 data points at least, right? We need some thousands of data points to do something interesting. And with those very, very high powered methods, you can't actually evaluate 1,000 times at all, right? There are people who engaged in doing one calculation for a very interesting system, and it takes 3 months. But that's one data point. So we're not going to do regression. But in time, maybe.
By the way, there is
I was wondering, you said the variance can tell you when it's working, when it's not. Is that generally true, or
No?
Because couldn't you just then? And you also said that everything's local with around 20 atoms affecting each atom, and you could run DFT in a minute on that new little cluster every time you got into one of those places. Is there a way to sort of?
So these are the 20 atoms. That was sort of locality for the very crude estimation of the accuracy. For these silicon examples, you need most of the cells are about 100 atoms.
Okay.
Not 20. The variance is interesting. We're thinking about that very, very actively. It seems to work well here in this silicon example, only after this is a very extensive data set. When we have a small data set, it works much less well.
Right.
And I think that's probably where our kernels could be improved. So it's well observed by machine learners that the mean that you predict is less sensitive to the kernel than the variance. And I think that our variance Our kernel might be good enough for the prediction of the mean, but significantly less good for the prediction of the variance.
Yeah.
And the fact that for a very large, very extensive, very comprehensive model, it's still okay, is kind of makes sense because I have so much data that improves the estimation of everything. But when we try to use the variance to build the model to see where we need to go in early stages, it's not.
Right.
But it's a very active area. People are very much thinking about that.
I'm just wondering if you've thought of running a local DFT to sort of fill in the gaps in the training data, kind of as you go.
Active learning, yeah, lots of people are engaged.
Okay, all right.
And to some extent we are too. That's where I'm torn between my machine learner friends and approximation theory friends, right? So the approximation theory friends tell you that you should just forget all that and try and get something that actually extrapolates properly. But then I go back the next day, and I agree with them. And next day I go back to my machine learning friends, and they say, no, you should do active learning and predict the error and take data there. Oh, sure. So, no, so there are various ways of doing docking. And this one was a very simple one to kind of see whether our kernel is sensible. This one was not a dynamical simulation. This was a classification. So here, the data is experiment. And you take, it's called the DUDE, and database of useful decoys, I think. And you take a protein and you collect from experiment whether particular drug-like molecules bind or not. And you say yes or no. And then then you can ask, can you actually then tell about, if I give you another 1,000, can you rank them based on that? And so with this SOAP kernel, this turns out to be really quite successful. So what you see here is the sort of the characteristic curve. Let me see if I can get my mouse back. So here, this is the sort of false negatives versus false positives in that ranking. So the perfect model would go straight up and across. And our average is really not far from that. This one is very funny because this is just one protein in that database where our answer is essentially random, right? So the false positives and false negatives come sort of equal. The x equals y line is when you know nothing. And we queried this after this result with the people who made the database, and they said, oh, sorry, there was an error in the database. And that's when they corrected it, then the curve is one of these black ones. But you're right, the thing we really would like to do is to build a force field and then actually do a simulation of free energy of binding. And that's a million time step simulation, you need the huge accuracy and so on, and we're nowhere near that. One of the things that this kind of classification can't do is actually get the rates. So the experimental data is very, very noisy, but there is experimental data on binding and unbinding rates. And when we try to regress that just based on the experimental data, that doesn't work so well. It's very, binding, yes, and of course there was an exponential thing, and that's difficult. But that's why we would like the force field, and I think that's one of the big targets, is to try and do that.
If you indeed have large systems, oh, sorry. Yeah, I was saying I didn't understand the answer to the question of François Boulanger, because you are saying, okay, the problem is extensive, so I can work on small pieces of 200 and then sum up. But if the problem was fully extensive, then there would be no problem. There are obviously...
Why would say there's no... What do you mean no problem?
Well, in the sense that...
This would work.
Yeah, I mean, you would just have the small piece and you wouldn't even worry about the big... I mean...
No, that doesn't mean you don't need to simulate with 100,000 atoms.
Yeah, so the question is, how are you going to get the simulation of the 100,000 to train the aggregation of your models?
No. There's instantaneous... Remember, this is dynamics. Imagine one of these. Imagine if I wanted to. This is a good example, which we haven't done with this model, but we would like to. Imagine this model. So what's happening here is that there's a strain field which concentrates the actually what happens here is over time is a function of the entire geometry. If I don't have this whole system, this is not going to be wrong. But instantaneously, as I solve the Newton's law, the force on that atom only depends on the 50 atoms around it, instantaneously. So it's okay to have a model that is where each atom only knows about 30 atoms, but you now need the big system because you cannot generate, you can't model this geometry. The same thing with the protein. I suppose it was the real world that each atom really only knew about instantaneously its 50 neighbors. I still have a protein and it still has some statistical property. It folds. It's a viral capsid. You change one of those atoms and over time the capsid unravels. Right? So you need the big simulation, but there is locality. Now, I know why you're asking this. There are some systems where this locality isn't there, or not so exact as I say. That's where Coulomb interactions and dispersion interactions are longer range. And that's where you and I have been discussing how to bring in the multi-scale nature of those parts of the interaction. I've been carefully avoiding them for the past 10 years, really focusing on systems where at least the energy instantaneously is local, but in order to, for example, do force fields for proteins, we will need a much better control over the Coulomb interactions and the parameters of them, which is not local.
Last question. Slide with the line of papers.
Yeah.
Just to understand.
That's right. And that's right. And actually, so these models, a lot of them are of the similar class. So they're all amorphous. And I said we need protocols. I don't have universal ones, but we're very interested in working on that. So we have protocols to say, what do you need to do if you want to model an amorphous system? And we run a quench from high tech. We start with random. We place the atoms randomly. We train a crude model. We start quenching it. It's complete garbage, but we keep reevaluating small systems, 100-atom systems. We keep reevaluating the reference and keep improving the model until the quenches don't change. And that protocol has, I think, 4 or 5 of these papers has that protocol in it. Now, that doesn't do everything. It doesn't do defects. It doesn't do surfaces. So it's not universal, but it's sort of on the way. That's right. So the carbon model is the first one. So the carbon model, which we used, is 2 years old, and we used it to study this growth of amorphous carbon films. And just a month ago, I was at a workshop where I was surprised to see other people. Several of the talks are using our model to do something they couldn't do before. The trained model, exactly. So all these models are published as plugins to standard molecular dynamics codes, and so people use them to. And actually, that's another thing that's kind of different, I think, from the machine learning community's normal mode of operation. That I'm interested in making these models and making a difference to materials modeling, but I'm not going to ever do the biggest materials simulation. I'm not going to be the person to do answer the big materials questions. My models are only as good as people who use them are. And we need to make models that other people use to do science. That, I think, is the right niche for me.